So we are taking the class 10 mathematics, and the first chapter is the real numbers. In class 11th we have already learned various aspects of real numbers, and also we have discussed about the irrational number. In this chapter also we are going to deal with the real numbers, but with a different perspective. We will see two very important properties of positive integers in various sections, and we'll call them Euclid division algorithm and fundamental theorem of arithmetic. First one, as the name would suggest, division algorithm is related to the divisibility of the integer, and we will see that a positive integer a when divided by any other positive integer b, then it will give us some remainder r which is smaller than b, and we'll see it as a division process only. And then, quite easy to understand, but this property is very important. How we can apply it? We'll see how to compute the HCF of two positive integers using this Euclid's division algorithm. Then we'll turn our attention to fundamental theorem of arithmetic. That is, it has to do something with the multiplication or the product of positive integer. And we already know with our previous discussion in class 9th that every composite number, it can be expressed in the form of multiplication of or product of primes in certain unique way. And quite easy to state this line, but deep need to understand. We need some more thoughts about it. So we'll use this fundamental theorem of arithmetic in various applications. We'll try to prove the irrationality of root 2, root 3, root 5. And also we'll try to see and explore what exactly and how exactly we can say that this p by q is terminating or non-terminating, means recurring decimal value. We'll see the prime factorization of the denominator of q, and by this how this q becomes will give us the idea of whether our division or decimal is stopping, or it has a concrete value, or it is going to repeat or non-terminate. We'll start with the Euclid division lemma. Let me present in front of you a story, a very interesting story. This story says that you have a seller who sells egg. Now what happens, a person comes, he is an idler, and he sees, okay, he is selling eggs, why not to mess with him? I don't have any work, let's mess with him. And they start some conversation, and that conversation becomes ugly, and they involve in a fight. And that after this tussle, the eggs of the person who is selling egg are broken. Now this man, the poor man who is selling eggs, he approaches panchayat and he asks the panchayat to give him or to ask this guy to return him for the loss. Panchayat asks, okay, explain, or how many eggs are broken, please explain us. So the way this gentleman explains the things is like this. He says, if counted in pairs means 2, 1 will remain. Means if 2 counting, then the remainder will be 1. If counted in pairs of 3 into 3 partitions means 3 eggs, 2 will remain. If 4 eggs, partition of 4 eggs or pack of 4 eggs, 3 will remain. Pack of 5, 4 will remain. 6, 1, 2, 3, 4, 5, 6, and it will 5 will remain, 7, nothing will remain. And one more thing is he has a basket, and the basket cannot accommodate more than 150x. It will not be more than 150x. So how to solve this puzzle? Now the panchayat has a very intelligent man in the group. So he starts, okay, we are going to solve it. How? First of all, he looks that, okay, the number of eggs are less than 150. Now he starts translating everything backwards. If the pack is of 7, nothing will remain. That means he chooses any number, say he has some p natural number. Then this a, if you say that a is the amount of numbers, or a is the number of eggs he has, a would be 7 into, say, some p natural number plus 0, means 7 packs, 7 into p plus 0 means nothing will remain if the packs are made in the 777 packs. The next one is if the packs are made in 6, means 6 eggs, 6 eggs, 6 eggs, if they are counted like this. After 6 are completed, means 5 will be remaining. Similarly, these, right? So if you see here that if we have a and b as some positive integers, b is taking the value as 7, 6, 5, 4, 3, 2, means 7, 6, 5, 4, 3, 2, and the remainder is 1, 2, 3, 4, 5 and 0. You see, always the remainder r is less than this b. This r is always less than this. This one is always less than this. So this is actually the Euclid division lemma. Now to solve it, you can easily think, and the person who is a great mathematician in the pack or in the panchayat, he started with 150. He started counting backwards, and at some point he started dividing it by multiples of 7, because after division by 7 means the pack of 7 exactly gives the remainder 0, so there will be no remainder. So if some number which is less than 150 is divided, it should give you the value as remainder as 0. So 119 is that solution. 119 by 7 is 7 1 is 7, 7 7 is 49, right? So this is there are around 17 into, you can easily say that the number of eggs are 119 and the packs are like 117. So let us consider some more view. That 17, 6, 5, 12, 24. So 17 can be written in the form of 6 into 2 plus 5. So 6 goes into 17 twice and it will give us remainder as 5. Similarly, if we take this one, 5 can be written as 12 into 0 plus 5. 20 can be written as 4 into 5 plus 0. So what we have done is, we have written each and every number in this form. All these are what we have discussed, means a is equal to bq plus r, but we have to remember this remainder is less than b but greater than 0. And one more thing I need to highlight, q and r can also be 0. Now let us turn our attention towards finding this q and r. So we have these say some pairs, and we have noticed that this q and r, they are unique. So there are only integers which will satisfy this equation. This is nothing but what we have seen up till now is just a read statement, or another way of stating the long division process, which we are doing for quite a few years now, and this says that the integer q and r are nothing but the quotient and the remainder. So let us give a formal statement. This is lemma. Lemma is a proven statement which is used to prove another statement. While the algorithm, these are well-defined steps or say a procedure to solve a particular problem. So Euclid division lemma, it says that if you are being provided positive integers a and b, so there must or there exist unique numbers q and r such that a is equal to bq plus r if r lies between b and 0. And we have known this for quite a few times. We have done this in the previous classes. Now we formalize it as Euclid's division lemma. Before I go ahead, let me tell you about Muhammad ibn Musa al-Khwarizmi. You will be surprised to know that the algebra or the algorithm all has come from his name. His famous book, or these are derived from his famous book, Hisab al-Zabr wal-Muqabla. He gave us all these things which we are studying right now. So Euclid division algorithm is a technique, or the application of this Euclid division algorithm can be used for HCF, highest common factor. Just recall or remember what HCF was. HCF was, or HCF of two positive integers a and b, is what? Is actually the positive integer d, or any integer d, positive integer d, which divides a and b both. Any highest number, positive integer, that divides a and b together, or means that it divides them, this is known as the HCF. If you want to see how this algorithm is going to work, let us take an example. Suppose you are given 455 and 42 as the numbers and you want to find out the HCF. So let us write 455 in terms of 42. So 42, this 455 can be written as 42 into 10, remaining is 35. 42 into 10 plus 35. Now, since the remainder is not 0, we'll take this 42 and again do the same thing. 42 is 35 into 1 plus 7. Again the remainder is not 0, we'll take 35. 35 can be written as 7 into 5. Now we have 0. As we see, the result has gone 0. This particular number 7 is our HCF. So without doing any that or those things which we used to do in our previous classes, just by applying the Euclid's division algorithm, we have found out the HCF of this number. So the algorithm can be defined or can be stepwise discussed like this. If you wish to obtain the HCF of two numbers, say any number c and d, and you need to see that c is less than d, because in these two numbers one has to be less, then what we do is we will apply the Euclid's division lemma for c and d, and we will try to find out the whole numbers q and r such that this equation applies. C is equal to dq plus r. R lies between d and 0. If r has become 0 somewhere, we will conclude that the HCF of this c and d is nothing but this d is the HCF. Otherwise, we will continue doing this by taking this d again and doing till the remainder becomes 0. And how this algorithm works? This algorithm works because the HCF of c and d will be equal to the HCF of d and r, right? So let us take some example of what we have learned. We will try to find out the HCF of 4052 and 12576. Because this is the greater one, let us write this in terms of 4052. So 12576 can be written in terms of 4052 like this: 4052 into 3 plus 420. Now we are left with certain remainder. So let us write 4052 in terms of 42 into 9 plus 272. Again we have got some remainder. So let us take 420. Write it in this form: 272 into 1 plus 148. 272 again can be written as 148 into 1, 124. So still we have not got the 0. Again 148 can be written as 124 into 1 plus 24, no 0. 24 can be taken again and 4 into 6 plus 0. That means we have got a 0. So this 4 is actually the HCF of these two numbers. And if you watch very closely, the HCF of this 24, 4, 124, 4, 148, 124, and if you go backwards till this point, they all are same. They are same. So it is not only useful, this Euclid division algorithm, for finding the HCF, but various other things, various other aspects where we apply it. So Euclid division lemma and algorithm, they are very closely interlinked, and that is why people often call these former as the division algorithm also. This can be called as division algorithm. Since this Euclid division algorithm is stated only for positive integers, it can be extended to all integers. This is not the point of discussion right now. We'll be taking it in the next classes. So Euclid division lemma algorithm, as we said, they have various applications. Let us see. We have to show that every positive even integer is of the form 2q, and that every positive odd integer is of the form 2q plus 1. Every even positive is 2q, every odd positive integer is of the form 2q plus 1. How we are going to do this? Let us take a. Let a be any positive integer and b is equal to 2. Let a be as a positive number and be equal to 2. We start with 2. Why we have taken 2? Because we see that 2 is here. In the question itself it is given. So by applying this Euclid theorem, a is equal to 2q plus say some r. A is equal to some. A is any positive integer, and this positive integer can be 2q. It can be equal to 2q plus 1. But a is equal to 2q plus r. This we have taken. And since we are given r is equal to 0 or r is equal to 1, and r lies between, r is between 0 and 2, and this is b, and we know that the remainder is always greater than 0 and less than b. Here 0 is this and b is 2. This is b. So a can only be, place one time 0 here, so it will be 2q. Place one time 1, so it will be 2q plus 1. This is how the equation goes. So a is the form of 2q, then a is an even integer, and also a positive integer can either be even or odd. That is why any positive odd integer has to be 2q plus 1. If you don't understand, let us take one more example. We have to show that any odd positive integer is of the form this and this. Again, we'll take a. A is a, say, any positive integer. And we again apply the division algorithm. Now here we take b as 4, because we see that 4 is at the 4 gives the direction to this number. So a we have taken is the number and b equal to 4, and we see that the r has to be between 0 and 4. The r has to be between 0 and b has been taken as 4. So what are the possible remainders? 0, 1, 2, 3. So a can be 4q, 4q plus 1, 4q plus 2, 4q plus 3. So what we have done here is, we have written it as 4q plus r. R can be 0, 1, 2, 3. So 4q, 4q plus 1, 4q plus 2, 4q plus 3, where q is actually the quotient. But if we take a as 4q and 4q plus 2, 4q divisible by 2, yes. 4q plus 2, take 2 common, 2q plus 1, again divisible by 2. So we cannot take these two. Why? Because they are divisible by 2. And we have been told that these are odd integers. So they can only be 4q plus 1 and 4q plus 3, because this cannot be taken. So any odd integer can be written in the form of 4q plus 1 and 4q plus 3. One more example we take. There is a sweet seller. She has 420 Kaju barfis and 130 Badam barfis. She need to place these in the form of stack. with same number, and she want to ensure that this tray, when she places this two, should take at least area as possible. Means he wants the space usage properly. So what is the maximum number of burfis that can be placed in each stack for this purpose? As we see here, it clearly shows that the question asks for the HCF of these two numbers, highest common factor. So we'll write 420 in the form of 130. So 420 can be written as 130 plus 3 plus 30. Take 130. 130 can be written as 30 into 4 plus 10. 30 can be written as 10 into 3 plus 0. And now we have got 0. So 10. This is the number. 10 is the HCF. So she ought to have the packs of these Kaju Barfis in the number 10. So this we have taken as the first discussion of real numbers. We will be taking few more, because very important next algorithm or what we are going to prove by taking it, that is P by Q form, irrationality, everything we'll see in the next discussion. Thank you so much. Take care of yourself.